Fire a single particle at a wall with two narrow slits. It lands on the screen behind as one dot. Fire another dot. Keep going, and thousands of dots slowly arrange themselves into stripes, the exact pattern a wave makes. One particle at a time, and the result belongs to a wave. Nothing in everyday life behaves this way. This is quantum mechanics, and by the end of this video, you will see how the same rules that draw this pattern also keep atoms stable, make lasers possible, and run the most precise clocks on Earth. Quantum mechanics is the set of rules that matter and light follow at the smallest scales. Electrons, photons, atoms, things roughly 1 billion times smaller than anything you can see. Down there, the everyday picture of objects moving along definite paths stops working, and a different rulebook takes over. The experiment you just watched, called the double slit experiment, is the cleanest window into that rulebook. So let's slow it down and find out what is actually going on. First, what should happen? Spray paintballs at a wall with 2 slits, and you get 2 piles of paint, one behind each slit. Particles travel one path each. Now send water waves through 2 gaps instead. Each gap spreads its own ripples, and the ripples overlap. Where crest meets crest, they reinforce. Where crest meets trough, they cancel. On the far wall, you get stripes, bands of strong waves separated by calm. So the test is simple. Particles make 2 piles. Waves make many stripes. Now, shoot electrons, single, tiny units of matter. Each one arrives at the screen as a single dot, at one place, at one moment. That is particle behavior. But the 2 piles never form. The dots build stripes, and some regions of the screen, including spots directly behind the slits, stay almost empty. Here is the strange part. This happens even when the electrons are fired one at a time, with nothing else in the machine to interfere with. Each electron lands alone, yet it still avoids the dark stripes, as if something spread out passed through both slits and steered where it was allowed to land. Here is the rule quantum mechanics actually gives. It does not track the electron along one path. Instead, it assigns a wave of possibility to each route the electron could take, through the left slit and through the right, and lets those 2 waves overlap. Where the 2 possibilities arrive in step, they reinforce, and the electron is likely to land there. Where they arrive out of step, they cancel, and the electron almost never lands there. This overlap of possibilities is what physicists call superposition. It does not mean the electron splits into 2 little objects. It means that until the electron is detected, its state genuinely includes both routes, and those possibilities interfere with each other like waves. The dot is real. The stripes are the map of where dots are allowed. So what happens if you catch the electron in the act? Put a detector at the slits that records which one each electron passes through. The moment you do, the stripes vanish. You get 2 plain piles, exactly like paintballs. Same slits, same electrons. The only difference is that the path is now on record. And this has nothing to do with a person watching. Measurement in quantum mechanics means a physical interaction that leaves a trace. If anything in the universe carries away a record of which route was taken, a detector, a stray photon, a single jostled atom, the 2 possibilities can no longer interfere. Just last year, physicists at MIT built the most stripped-down version of this experiment ever, using 2 individual atoms as the slits, and confirmed the trade-off Einstein and Bohr argued about a century ago. The more path information exists, the weaker the stripes become. You can have partial information and faint stripes, or full information and none. The rulebook is exact about the exchange. Which raises the obvious question. If superposition is real, why do you never see a coffee cup in 2 places? Because big things cannot keep their possibilities private. A dust grain sitting in air is struck by billions of air molecules and photons every second, and every collision carries a little record of where the grain is out into the environment. All those tiny records act like path detectors. The interference between the grain's possible positions washes out almost instantly. Physicists call this decoherence, and it is the main reason quantum behavior hides at human scale. To be honest about it, decoherence explains why we never observe the interference, but physicists still debate exactly why each measurement gives the single outcome it does. What it tells you in practice is simple. The bigger and warmer an object, the faster its quantum possibilities leak away into the world around it. If this were only about electrons and slits, it would be a lab curiosity. But this rule book built the world you are sitting in. Start with atoms. An electron bound to a nucleus is a confined wave of possibility. And a confined wave can only vibrate in certain fixed patterns, the way a guitar string of a given length can only play certain notes. Those fixed patterns are the atom's energy levels. They are why atoms do not collapse, why each element glows in its own exact colors, and why every cesium atom in the universe is identical to every other. Chemistry, light, and the stability of matter all come from possibility waves locked into standing patterns. A laser is that energy ladder put to work. Pump energy into a crowd of atoms, and you lift their electrons onto a higher rung. When a photon with exactly the right frequency passes one of those excited atoms, it triggers the electron to drop, and the atom releases a second photon that is a perfect copy of the first. Same frequency, same direction, same rhythm. Put mirrors at both ends so the photons sweep back and forth through the crowd, and one photon becomes two, two become four, until an avalanche of identical photons pours out through one mirror. That is why laser light stays in step and holds a tight beam. Every laser, in eye surgery, fiber optic internet, barcode scanners, is quantum copying, run as an avalanche. Now push the precision further, because the official definition of a second is quantum mechanics. Every cesium atom will absorb microwaves at one exact frequency: 9,192,631,770 cycles per second, and at no other. Atoms cannot drift, wear out, or be manufactured slightly wrong. Nature builds them all identical. So an atomic clock tunes a microwave beam until cesium atoms respond, and then simply counts the cycles. Count that exact number, and 1 second has passed. The newest American fountain clock, switched on in 2025, keeps time so precisely that it would drift by less than 1 second over 100 million years. When your phone shows the time, it is synchronized through layers of infrastructure to atoms doing quantum mechanics in a lab. And here is the elegant reversal. The same fragility that erases stripes in the double slit, the fact that the tiniest disturbance leaves a mark on a quantum state, is exactly what makes quantum systems the most sensitive detectors ever built. Anything that nudges an atom's energy levels, even slightly, shifts its behavior in a way you can count. A magnetic field does it, gravity does it, acceleration does it. So engineers have turned atoms into instruments, chip-sized atomic magnetometers, small enough to hold, that can sense the faint magnetic whisper of a human heartbeat, and falling clouds of cold atoms that measure gravity precisely enough to notice what is buried underground. The thing that makes quantum states hard to protect is the very thing that makes them worth listening to. So, what is quantum mechanics? It is the rule book underneath everything. Possibilities spread out like waves, overlap and interfere, and the world takes a record. sharpening them into single, definite events. You never see the wave itself. You only ever see the dots it leaves behind. But watch the screen long enough, and the pattern is undeniable. Every stable atom, every laser beam, every tick of official time is the same message repeated. The rules down there really are different. And they work.